Hello Bobcats. In this video we will be covering more gas laws, specifically gas stoichiometry, how to determine molar mass and density of gases and partial pressure of gases. And so you can find this worksheet also in the gases resource page called Gases PowerPoint or PPT Practice Problems Number 2. Now in the last video I got cut off, and so I'm going to go ahead and do this last problem that was missed on the last video, and it's an ideal gas law. So again, we remember ideal gas laws that's a PV equals nRT. That's the ideal gas law. And how do I know when to use an ideal gas law? It's when I only have one of the variables. Now if I had two volumes or two temperatures or any of those, I wouldn't use the ideal gas law. I would actually use the combined gas law. But in this case, as I look at it, it says calculate the number of moles, so that's going to be N, of oxygen gas in a 2.6 liter container of 19 degrees Celsius. Now remember, that's the temperature, but we're going to have to change Celsius to Kelvin. And then 755 torr, that's pressure. So there's my NVTP, there's my four variables, and I'm looking for N. So let's make sure we got everything to match. Now remember, the R, the gas law constant, is 0.0821 liters atmospheres per mole Kelvin. Okay, so again, I notice that I've got liters, that's correct. I don't have Kelvin, so I got to convert my temperature from Celsius to Kelvin. And then my pressure is in torr, so I have to convert that to atmospheres. All your units have to match what's in R. So again, temperature would be 19 plus 273. So that comes out to be 292 Kelvin. That's my temperature. That's a K. Didn't look too good there. And my pressure, we have 755 torr. And to convert that, we know that 1 atmosphere is equal to 760 torr. So the torr cancels, and so my pressure is now in 9.993 atmospheres. So now I have all my units match. We write the original equation, which is PV equals nRT, and I am going to isolate, in this case, for N, the number of moles. And so when I do that, I divide both sides by RT. So N is equal to PV over RT. Now I'm going to substitute and solve. So my pressure is 0.993 atmospheres. My volume is 2.6 liters. 2.60 liters. My next one is the R, so I'm going to put in R, and it's on the bottom now. So R is 0.0821 liter atmospheres mole Kelvin. So I have flipped the units. So liters are gone, atmospheres are gone. And then temperature is on the bottom. So I'm going to put the temperature of 292 Kelvin. Now Kelvin is gone, and all that's left is moles, and that's what I'm looking for. So when I put it in the calculator, it's going to be 0.993 times 2.60 divided by 292 divided by 0.0821. And that comes out to be 0.108 moles of gas. Now again, if you're having trouble seeing the equation when I use the dimensional analysis, this is just PV over RT. It's the same equation, PV over RT, or TR. So that's the ideal gas law. Now we're going to use the ideal gas law for gas stoichiometry. And when do you decide, how do you know if you're doing a stoichiometry problem? Well, whenever you have a reaction, and we have a reaction right here, we are going to be doing stoichiometry. So, and the best way to solve problems with reactions is to write the information under each of these substances, the reactants or products. And so as I go through and start identifying, I'm going to use red this time. It says the reaction used in the deployment of automobile bags is the high temperature decomposition of sodium azide to produce nitrogen gas. How many liters of nitrogen gas, so that's what I want, how many liters, so I put it underneath nitrogen gas, at 1.5 atmospheres, so the gas, the nitrogen gas is at 1.5 atmospheres, so I put it underneath the nitrogen, and a temperature of 30 degrees Celsius. Now I'm going to add 273 to that because it's got to be in Kelvin, so that's going to be 303 Kelvin. That's all for the nitrogen gas. So we want to know how many liters of nitrogen are produced by decomposition of 45, so that's 45 grams of the sodium azide. The next thing to do would be to just make sure we have the variables, what variables we have. So this is going to be a volume variable, this is pressure, and this is temperature. Well, I'm also missing the number of moles in this. So in this case, I have to find the number of moles before I can use the equation. You cannot use PVNRT, PV equals nRT, for gas unless you have 3 of the 4 variables. So I've got 2, I need to find the third one. And the best way to find N, or the only way to find N in this case, is to convert the grams of sodium azide to moles and do a mole to mole ratio, and that tells me how many moles of gas I have. So that's the first thing I'm going to do. So we're looking for how many moles of nitrogen gas. So let's do stoichiometry. So that's 45.0 grams of sodium azide. And to convert it to moles, we're going to say 1 mole. We're going to use molar mass. Go to the mole. Remember that? Molar mass of sodium azide, 1 mole, is a mass of 65.02 grams. So that's the molar mass of sodium azide. Now you notice here, we don't want moles of sodium azide. We got to get to moles of nitrogen gas. So that's 2 to 3. So it's for every 2 moles of sodium azide, I'm going to produce 3 moles of nitrogen gas. Okay, so now that gives me the number of moles. So when I calculate that, that's 45 times 3 divided by 6.02 divided by 2. That's going to be 1.038 moles of nitrogen gas. Okay, now I have N. So this is N right here. So now I've got N. So I've got 1, 2, 3 of the variables. So now I can use PVNRT. Let's rearrange it. I'm looking for the volume. So I'm going to isolate for volume. So volume is equal to nRT over P. I divide both sides by P. So the second part then is to find the volume. And again, I'm going to do my dimensional analysis format. N, we found that. That's 1.038 moles of nitrogen gas. And now we have R, so that's 0.0821 liter atmospheres over mole Kelvin. Moles are gone. And we want T next, and my temperature is 303 Kelvin. And then P on the bottom, which is 1.15 atmospheres. Kelvin cancels, atmospheres cancel. I'm left with liters. That's a volume unit, and that's what I'm looking for. And this comes out to be 22.5 liters. All right, so that is stoichiometry. In this case, we had to do stoichiometry to convert the grams of sodium azide to the moles of nitrogen, which will then give me N. And I now have 3 of the 4 variables, and so I can find volume by multiplying number of moles times the constant times temperature divided by pressure. Let's look at the next problem. It's another stoichiometry problem. And again, I know it's stoichiometry because I have a reaction. So let's identify all of the information. So as I go through this, it says how many moles. So we're looking for the number of moles of mercury 2 oxide. This is mercury 2 oxide, so I want to know how many moles of mercury 2 oxide must be thermally decomposed to produce 2.26 liters of oxygen gas. So there's my oxygen gas at 1 atmosphere. That's my pressure, so 1 atmosphere, and a temperature of 23 degrees Celsius, so add 273, and so that's 296 Kelvin. Again, I'm going to identify all my variables. So we have volume, pressure, temperature. In this case, the fourth variable that I'm missing is N. But because I have 3 of the 4, I can use my equation, my Pivnert, to find N. So let's do that. We got PV equals nRT. We're looking for N, you'll notice here, so let's divide both sides by RT. So N is equal to PV over RT. Okay, so let's do that equation. N in this case is going to equal to my pressure, which is 1 atmosphere, my volume, which is 2.26 liters. Now on bottom I have R, so we got to put R in the bottom, 0.0821 liter atmospheres, and then of course I got to flip the unit, so that's mole Kelvin. Now if you notice, atmospheres are gone, liters are gone. I have Kelvin. Now I just need to put the temperature, and so if you look here, I've got an empty space, so that's where I'm going to put my temperature, 296 Kelvin. Kelvin cancels, and so moles are where I'm looking for, and this happens to be moles of O2. Remember, we're doing the gas, so we got to make sure we're looking, you know, this is moles of O2. When I multiply and divide, that's going to be 0.0930 moles of O2 gas. Now if you're having a hard time seeing the equation, remember this is PV over RT. Okay. Now that I have moles, I can do stoichiometry and figure out how many moles of mercury I have. So question mark, I want to know moles, it's mercury oxide, sorry, of mercury 2 oxide. Not just mercury, mercury 2 oxide. Well, I'm going to start out with 0.0930 moles of O2 gas. And now I'm in the moles, so I'm going to convert from moles of O2 to moles of mercury 2 oxide. So it's a 1:2 ratio. So for every 1 mole of O2, I'm going to produce or need to react 2 moles of mercury 2 oxide. Let me say that again. So for every 1 mole of O2 produced, I need to react 2 moles of mercury 2 oxide. Now, a lot of students just keep on going, but remember, that's why I write what I'm looking for, so I know when to stop. That's what I have, that's what I'm looking for. So I just multiply by 2, and I get 0.186 moles of mercury 2 oxide. Now, the one thing I want to make sure we understand, how do you decide when you're going to do the stoichiometry first or the equation first? Well, the easiest way to do that, again, is to make sure you write everything down, identify your variables, and if you are missing two variables from the Pivnert equation, you cannot use the equation. So you have to do stoichiometry first and figure out how many moles from a stoichiometry problem you have. And then you can use the equation. So, and remember, this equation here, this is N R T over P. So in this case, I did stoichiometry to find the moles, and then I'd use the equation. Now, when I write out all my variables and I'm only missing one of the variables, then I use the equation to find that missing variable and then do stoichiometry. So that's how you make the decision on which one's first. Let's keep going. The next thing we have is partial pressures. So remember, partial pressures is just taking all the pressures and adding them up to be the total pressure. So all the pressures of the gases in a system adds up to be total pressure. But part of that is knowing that we're going to have what's called a mole fraction of the gas, and let's just say, let's look at O2 just because that's what we breathe. Mole fraction is equal to the number of moles of that oxygen gas, or the gas we look at, divided by the moles of the total gases. Now, this also equals the partial pressure of the oxygen gas over the pressure of the total system. So that's an equation we're going to really look at and use right now. Now, the mole fraction of oxygen in a scuba tank is 0.21. In other words, we breathe, our atmosphere has 21% oxygen, so it's got a mole fraction of oxygen as 0.21. Now, a scuba diver wants to have pretty much the same partial pressure or mole fraction of oxygen in his scuba tank. So he's got to make sure that whatever he puts in the scuba tank, he's got at least 0.21 mole fraction of oxygen, or percent oxygen if you want to think of it that way. We want to know what is the partial pressure of oxygen in atmospheres in a scuba tank with a pressure of 3,100 psi's. Now that's really high. And that, you know, the pressures of scuba tanks are very high. So let's put the equation. If I take this, and we know that that mole fraction is equal to the pressure of O2 over the total pressure, and I multiply both sides so that I can just get PO2. The partial pressure of O2 is equal to the mole fraction of O2 times the pressure of the total system. So in this case, we already know the mole fraction, 0.21, which is basically saying 21%. So 0.21, that's this, times the total pressure is 3,100 psi, and when I multiply that, I get 651 psi's, pounds per square inch. That's how much oxygen pressure there is in the tank. But we want to do it in atmospheres, so I'm going to use this equality statement to convert. And so 1 atmosphere is 14.7 psi, pounds per square inch. That cancels, so this comes out to be 44 atmospheres is the partial pressure of oxygen in that tank. 44 atmospheres, that's pretty high. Now a lot of times you don't actually know the mole fraction right off. This time up here we did, because that's what we breathe, 21% oxygen, so you want that much. But here, let's look at the next one. Now we just know the number of moles of each. So I have moles of argon and moles of carbon dioxide. So looking at this up here, we know that we can find the mole fraction by taking the part divided by the whole. So my mole fraction of, CO2, not just O2, is equal to the moles of carbon dioxide divided by the total moles in the system. So we have 3.5 moles of carbon dioxide divided by 5.0 moles total. Remember, we add those to get total. 3.5 plus 1.5. That comes out to be 0.70. So that's the mole fraction. Or you can think of it as 70% carbon dioxide in that system. Now the total pressure is 7. So if I look back up here at this equation, the pressure of the carbon dioxide in that system is equal to the mole fraction of carbon dioxide times the total pressure. So that's going to be 0.70 times 7.0 atmospheres. That's the total. And that comes out to be 4.9 atmospheres. Okay. So that's the partial pressure of carbon dioxide in that system. And so that's a part of how we're going to use partial pressure. Now the next thing is molar mass and density of gases. So molar mass equation, if I remember and you have to remember your equations for the test. So molar mass equation is molar mass of a gas is equal to the mass of that gas times the constant times the temperature divided by pressure and volume. Now, when I know the equation, it's very simple. There's M, that's 25 grams. R is the constant, which we know is 0.0821. There's the volume, so there's volume. There's the atmospheres, and there's the temperature. So you can plug and chug and do this. Now, if you're having a hard time remembering all your equations, you can also do this by just looking at dimensional analysis. So let me show you how I do that. We're looking for the molar mass. So we know that the molar mass is in grams per mole. That's what we're looking for. Grams per mole. So when I look up here, I go through here, there's my mass unit. So I'm going to put that down, and I'm going to put it on top because I have grams on top. So now I have my grams unit that I need. Now the next unit I'm looking for is moles. Well, there's not moles there, there's no moles there, but we do know that R, remember R, is equal to 0.0821 liter atmospheres over mole Kelvin. Well, R has the mole unit. So I'm going to use R next, and I'm going to make sure that the mole unit is on bottom. The mole unit is on bottom. So that's going to be 0.0821 liter atmospheres over mole Kelvin. Now I have grams per mole. I have the units that I want. So I'm in good shape for those units. I just have to get rid of the 3 other units. Well, let's start off. If I have Kelvin on bottom, I can get rid of Kelvin by using the temperature. And so that's going to be 273 Kelvin, and I got that by adding 273 to 0. So Kelvin is gone. I need to get rid of liters. It's on top here, so I'm going to use this liters. Put it on bottom so I can cancel the liters. There's liters. That's gone. And then I have atmospheres on top. So I've got 1 atmosphere, so I put that on bottom. And atmospheres cancel. And if you'll notice, I have grams per mole. So that is what I'm looking for. That's all I need to do. So I multiply 25 times 0.0821 times 273 divided by 3.83 divided by 1. So that's going to equal to 146 grams per mole. And that's how we do it. Now, if you can remember the equation, you can just plug and chug the equation, and that's good. But if you can't, use your units. And remember, R has the units you're going to need. The next equation, the next one we're going to do is density. So let's find density. Now, the density equation is density is equal to molar mass times pressure divided by RT. Now, if you remember the equation, it's not too difficult. First, let's make sure we know we have molar mass. Now, there's no molar mass given here, but we do have the compound. And so I can get the molar mass of the compound. So that's 3 times 34.45 plus 1 times 1.01 plus 1 times 12.01. I add all of those up, and so my molar mass is 119.37 grams per mole. The next one, this is my pressure, but I'm in millimeters of mercury, and remember, R has atmospheres. Remember up here, atmospheres. So I have to convert millimeters of mercury to atmospheres. And I'm not going to show that work here, but I'm just going to do it. It's really 200 divided by 760. So that is 0.263 atmospheres. And then this is Celsius, which we've got to convert to Kelvin. So that's going to be 298 Kelvin, because I added 273 to that. Okay, now I have my variables. So I can just plug and chug. We've got 119.37, pressure 0.263 atmospheres, R we know it is 0.0821, and then T is this. But if you can't remember the equation, the best thing to do is this. The density unit, that's what we're looking for. So the density unit is grams per liter for a gas. Not grams per milliliter, but liter for a gas, because gases are much less dense. Now, I've got to get my gram unit on top. And the only thing that has grams in it is this, the molar mass. So I'm going to put that in, 119.37 grams per mole. Okay, good. I've got grams on top. The next thing is I need liters. Well, I don't have liters in these three variables, but I do have liters in my R. Liters right there. So I'm going to start. And by the way, remember, here liters are on top, but I need them on bottom. So I'm going to put it on bottom, 0.0821 liter atmospheres mole Kelvin. Okay, there we go. Now, if you'll notice right away, we've got grams per liter. There's my units that I need. Moles cancel. So the only thing I have to get rid of now is Kelvin and atmospheres. Well, we have Kelvin right here in our temperature. If it's on top here, I'm going to put it on bottom here. 298 Kelvin. And then atmospheres are on bottom, so I'm going to put them on top. 0.263 atmospheres. And that cancels. So I have, if you'll notice real quick, I have grams per liter. There's my units that I want. So when I multiply and divide, I get 1.28 grams per liter is the density of that gas. Now, real quick, to go back and show you how those numbers can be plugged in, we have P over RT for that one. And I forgot to do it up here, so let's do that. This is M, there's M, this is R, T over P, V. And so the equation works out. But I just use units. It's much easier. Now the last one is Graham's law. Now, Graham's law talks about the rate of effusion, and it helps us know, we can figure out molar masses if we know how fast a gas will effuse through a porous barrier. And so what we're going to do is solve this problem using the Graham's law equation. Now, Graham's law equation is the rate of effusion of, in this case, we're going to look at methane. So we're going to look at the rate of effusion of methane, CH4, over the rate of effusion of, let's see, same number of an unknown gas. So that's the rate of effusion of an unknown gas, and we'll call that X. Now the rate of one over the rate of the other is equal to the square root of the molar mass of X. So we got to make sure that they're at a diagonal. So if X is on bottom, we're going to put it up top, over the molar mass of methane in this case. Okay, so that's the equation. Now, I don't know if you remember this, but rates are always something over time. So you can say speed is distance over time, how much distance is covered over a certain amount of time. We can also say the rates of a reaction is how much there is a change in concentration over time. So here is my time unit for the methane. So we're going to say the rate is 1 because it says equal number of molecules. So let's just call it 1 molecule. Okay, so 1 over 1.50 minutes. That's the rate of methane. Over 1 over 4.73 minutes. That's the rate of X. Okay, and then we're going to say this is equal to the square root of the molar mass of X, and we don't know what that is, divided by the molar mass of methane, which, oops, I got ahead of myself. The molar mass of methane is 16.04 grams per mole. Okay, so there's molar mass of X. We don't know, but we do know the molar mass of methane. So if I'm going to come up here and I'm going to say, well, take 1 divided by 1.5, that's going to be 0.667 divided by 1 divided by 4.73 is going to be 0.211, and that's going to equal to the square root of the molar mass of X divided by 16.04. Now, if I take those two numbers, 0.667 divided by 0.211, so 0.667 divided by 0.211, that gives me a ratio or a number of 3.16 is equal to the square root of the molar mass of X over 16.04. And then how do you get rid of a square root? We multiply, or we square both sides. So I'm going to square this and I'm going to square that. When I square 3.16, I get 9.99. And when I square this, that will be mx over 16.04. And then I'm going to multiply both sides by 16.04. So the molar mass of X is equal to 16 times that is going to be, when you round it, actually when you multiply it, let's do that, 19, that's going to be times 16.04. 9.99 times 16.04 gives me a molar mass of 160.28. And remember, we go 2 decimal places for all our molar masses. So there we go. The molar mass of the unknown gas is 160.8. And that's it for our practice lecture video. And have a good day.